So here we're going to be looking at the tidbits bias variance.r script. And what we're looking at here is just a collection of examples and graphs that will give us some idea about the bias variance decomposition, some visual impressions of it. Now you can of course go through this code, but in this case, this is not exercise code. It's code that you can look at if you want to see how this was done, but there's no need for you to do so. Now, we start off, we generate this graph here, which is an idealized bias variance graph. So we have on the vertical axis the expected error, and on the horizontal axis the complexity. We see the expected error comes in essentially three forms. The bias, the blue line, starts off high for a simple model, decreases as the model gets more complex. Variance starts off low for a simple model, increases as the model gets more complex. And the irreducible error, which stays the same throughout. And then the purple line is the total error. Now, when we're trying to find the optimal statistical model or the optimal level of complexity of the statistical model, what we want to do is to find the minimal total error. We want the complexity of the model to hit the sweet spot where we reduce the sum of the error due to bias and the error due to variance. In this case, we get this horizontal black line and we see where it is. Now, what's important is that in this graphic, we're holding the amount of data we're working with static. Now, we can change the complexity of the model, but this of course involves a trade-off. We can reduce bias, but only by increasing variance and vice versa. But we can reduce bias and variance together if we manage to get more data. So we can see what would be expected to occur if we were to get more data. And here, we're going from the previous graph is now in the dashed lines, and with this increase of data, we move to the now solid lines. And as we would expect, when the amount of data increases, the optimal model that we want becomes more complex. We see, of course, that as well, the total error has reduced as we get more data, and the complexity of the model associated with the optimal complexity is more complex. If we're thinking in terms of the result of training a model, and finding the minimal total error is what we're aiming for, a situation where we find a model that is to the left of the optimal location, that is to say a model that has higher bias and is simpler, is a situation where we're underfitting the data. The model that we're working with, the form of the model is not complex enough to capture the patterns that we're seeing in the data, the patterns that represent the function in the real world we're trying to model. And on the other hand, if we end up with a model that's to the right of the optimal model, that is to say a model that's more complex, we're going to end up overfitting to the data. We're going to end up having a model that essentially ends up fitting to the noise it finds in the training data rather than to patterns that are representative of not just the training data, but the entire population data that can be generalizable to new data cases. So here we've left unspecified what the measure of complexity is. We just have complexity here. In this course and in general, it's very common to use the number of parameters in a statistical model as the measure of complexity. Now, this actually works perfectly for linear models. It does not work unproblematically for nonlinear models. Now, for example, there can be very simple nonlinear models, simple in the sense that they have only a small number of parameters that are able to massively overfit on data. And here's a very small example. This is a cosine model with 2 parameters, And we are capable of fitting that, overfitting that, in fact, to any size data set. Essentially, the nonlinearity here gives us a degenerate case where we're able to overfit a 2-parameter model on any data. It will just give us smaller and smaller cycles in the cosine so that it can run through every data point. So this is just a bit of a warning, really. This measure of complexity when we're working with nonlinear models, this idea that the number of free parameters is a good measure of complexity, is imperfect. It generally works very well, but there are cases where it will break down.